Last lecture, we saw that phase lock loops are used for creating periodic signal. So in this lecture, we will see the qualitative functionality of this phase lock loop, and then we will also focus on the phase detector part, because it is this circuit which allows this loop to get locked. That means achieve the equation in the frequency domain. Output frequency is equal to n times of the reference frequency. So first we will see the block diagram of a PLL. Then briefly we will see the classification of PLL, and then see the qualitative functionality of PLL. So here we saw that there are 4 building blocks in a PLL. Phase detector, loop filter, VCO, and divider. So here we have output of frequency omega or F naught, and output actually will be a voltage, as was pointed out. And here the input to PLL is going to be a periodic waveform of, say, frequency omega r, and this will be basically voltage VR feeding to PD. And then from divider we will have frequency omega r or voltage omega d, and here we will have error, phase error. So we can label all these in terms of phase also, because it is this quantity which will be responsible for producing a voltage ultimately, which will be fed to the VCU. So this loop can be implemented in various ways. So there are 4 classes of PLL based upon the nature of these signals involved here and other location in the loop. So the first is analog PLL. So here in this implementation, the all signals and hence all blocks are analog. Second is digital PLL. So in this case, the phase detector, although the name might convey that all the blocks or all the signals are digital, but it is actually, phase detector is a digital circuit. So we will see that why we want to use digital phase detector. So it has advantage over the analog version. And this type of PLL can also be called as mixed signal PLL, because other signals might be analog. Then we have all digital PLL. So here, as the name suggests, all the components are digital. And then the fourth one is software PLL. So here, as the name suggests, when this PNL functionality is implemented using software on a microprocessor, so then we have software PLL. So what we will study in this course is mostly this digital PLL or even all digital PLL. But here we are going to focus more on the phase detector part. So here we have labeled the various signals VR, VD, and then VO, and ultimately we will be interested in a signal which will be fed to this VCO, and this is also sometimes called as the average of the PD and loop filter combined. So since we will be talking this VE bar signal, so we can represent the entire PLL using three blocks only, where the loop filter has been merged with the PD. So this is PD plus loop filter. And what we get here is average or the low frequency component of the actual signal that is produced by the PD. So here we are going to have these signals. VR is going to be A sine omega RT, which will be representing as A sine theta R. So this theta R is phase. Similarly, VD is going to be, say, B sine omega dt or equal to B sine theta d. And the output, of course, is C sine omega naught t equal to C sine theta O. And we know that this relation will hold true between these frequency components. And relation is going to be omega output is going to be n times of omega r. So here we have labeled a signal VE bar. This is a very important signal. So this VE bar actually is going to be a voltage which will be proportional to the phase error between reference signal and the divider signal. So from this PD plus LP block, we want a signal which will be fed to the VCO, which will ultimately allow this equation to get implemented. And this equation also implies that omega r is equal to omega naught by n, which is equal to omega d. So fundamentally, the equation which actually gets implemented is omega r is equal to omega d. That is the frequency of the divider and the reference, they are going to be equal. So it is this thing that gets implemented. And here we see that the V bar signal is getting fed to VCO, and we have already seen that the output frequency of VCO is given by this. It will be controlled by the input voltage, which is VE bar, and we had already seen this will be equal to omega C plus K, and here K is VCO sensitivity into VE bar. So it is this kind of relation that will be followed by the VCO. So here is output frequency, here V is bar, and we will get this kind of output. So now first we will see that how qualitatively this loop is able to uh, ensure this equation. That means ultimately make omega d equal to omega r. So we are going to take two typical scenarios, and then we will try to see that how this so-called locking. So this means locked state of PLL. So how this PLL gets locked, ensuring this equality. So we take examples. So we have suppose two signals, and in this case, let us say that omega r is greater than omega d, right? And we can also assume that phase is also greater than phase d. So this will be simple scenario, but the second condition might be different also. But the first condition is the main condition. That means there is a frequency difference between these two. So here we see that we will have a positive phase error using theta here. So there is a positive phase error in the beginning, and hence this the average voltage that will be produced is also going to be positive. Now we know that the VCO is going to function as per this plot. Now let us see that how this loop will be able to ensure that this frequency ultimately becomes equal to omega r. That means this also increases. So this scenario we will represent in form of circular motion, and from there we will try to interpret or see the functionality of this PLL. So what we have shown here is there is positive phase error. That means at t is equal to 0, say we have this scenario. So this is so phasor r, and this phasor r is rotating with omega r, and at t is equal to 0, it has a phase of theta r. Now at the same moment at t is equal to 0, we have another phasor omega d, and this has a phase of theta d. So here we can see that we have a phase difference of theta e given by this method. So this is the condition, and we want to see that how this PLL will be ultimately able to increase this omega d frequency so that it becomes equal to omega r. So at t is equal to 0, we might have this scenario that we have the error voltage given by this voltage. So there will be certain omega naught 1, and corresponding to this we will have omega d. So omega d is given by this equation at t is equal to 0 when the circuit is switched on, or when we start analyzing this. Now here we see that as t increases, as the time passes, since this omega r is moving at a faster rate compared with omega d, so this theta e, the error is going to increase. So as the time passes by, this theta e is going to increase. So when the theta e increases, what we find from this equation is that the average voltage produced by phase detector and loop filter block as a combine is going to produce more voltage. Now what happens here is you can see this on this plot that as time passes we will be moving in this direction because VE bar is going to increase. So when the VE bar increases, what happens is that the output of this VCO is now going to produce a frequency omega naught 2, which is going to be greater than uh, omega naught 1. Output of VCO is going to be omega naught 2, which is greater than omega naught 1. So in this way, we see that this implies omega naught goes up, and this ultimately implies omega d will also increase. So here we see that if we have this kind of scenario where the reference frequency is higher compared with the difference divider frequency, then the phase difference between two signal is going to increase. That will result in more voltage getting inputted to the VCO. That will ramp up the output frequency of the VCO, so that this omega d also ultimately increases. So here we see that as long as the frequency of omega r is more than omega d, this phase error is definitely going to increase with time. So that means VCO will definitely continue to get more voltage, and hence this omega d will continue to increase. So this way you can see that ultimately omega d will be able to catch up with omega r. And finally, what will happen is omega d becomes equal to omega r. So in this case, so then we will have this scenario that here we have omega d and here we will have omega r, and both are now rotating with same frequency or angular velocity. So that means this phase error is now going to become constant. And in some of the special cases, this also might be equal to 0. So this will happen only in rarity, but in general, this is what will be guaranteed. So this is how qualitatively this PLL will be able to ensure the frequency equality, or in other words, PLL will get locked. So here we had this condition that the reference frequency was more than the divider frequency. Now we can consider the second case where reference frequency is smaller than the divider frequency. Not only that, um, we can also take that the phase of reference is also less than the phase of divider. And now we want to see that how this will lead to the locking of the loop. That means omega d will slow down and it will become equal to omega r. So keep in mind omega r is fixed. We cannot alter it. It is omega d which can be altered by the loop. So here we can now see the scenario in the circular motion form. So what we have here is now uh, here we have omega r, which is rotating at a slower angular velocity. And then we have omega d, which is rotating at a faster angular velocity. So here we have theta d. So here also we see that the phase error between the two phasors, which is theta e, is going to increase with the time. So here the phase error, which is theta r minus theta d, is of course negative, and this is going to increase with the time. And here we see that this will lead to a voltage to the VCO, which is going to be negative, less than 0. So here, as t increases, so this is the scenario at t is equal to 0. So as t increases, what will happen is This omega d is, it is moving at a faster speed, so this theta e is going to grow, but it will grow in negative direction. So as this goes up, this theta e is going to decrease. That means in a negative sense, its magnitude is going to increase, but sign is negative. So we say that it decreases. That means it becomes more negative. So if you see the VCO characteristic, then this is the plot for VCO. So here we see that at t is equal to 0, for example, we will be operating here at this moment, and this will have a frequency omega 1. So this is at t is equal to 0. So now as time passes, this V will become more negative, say here. So this is VE2, this is more negative. And now you can see that this will decrease the frequency to uh, omega 02. So it will basically slow down this omega d. So it will reduce the uh, angular velocity. So this more negative phase error implies more negative voltage, and this will then imply uh, output decreases, the output of VCO decreases. This implies that the divider frequency also goes down. So here we will see that now this error will increase, but now it will increase at a slower rate. So in this way, ultimately, the VCO frequency will be able to uh, become equal to the reference frequency. Finally, this omega d will become omega r after some time. So this after a delay. So this how much time it takes will be decided greatly by the loop filter. That means what kind of V signal is being fed to the VCO. And this locking phenomena, that means this omega d ultimately becoming equal to omega r, might not be in a very smooth fashion. So this might happen after a certain uh, back and forth oscillation. Say, for example, if this is omega r, which we want to track, and this is time. So omega, this is frequency axis. So sometime it might track in this way, or sometime it might go and converge in this way. So what will be the nature exactly will be decided by the loop filter. So this is how qualitatively this phase lock loop ensures that the two frequencies are equal by processing the phase error between them. So we see that the phase error is a very important building block of this phase lock loop. So we will now spend some time on this building block. So this phase detector, this is broadly classified into two classes. First is analog, second is digital. So first we will see that how these analog phase detectors they can be created. So whatever may be the way of implementing this phase detector, ultimately what we want is uh, error signal, phase error signal given by this equation, and finally with the help of loop filter, this equation gets converted into this form. That means a voltage proportional to the phase error. So the phase detector must do certain mathematical operation on the two signals which are going to be in voltage form, and they can be sinusoid or square, such that this quantity comes into existence, difference of the phase error. So if you recall the mixer or the multiplier, so that circuit basically can do this part. That means it can produce this kind of output. And then the loop filter will be able to take care of this part, second part. Let us see that how this mixer will be able to produce the phase error or detect. So mixer can be used for the analog phase detection. So here we know that in the mixer we feed two signals. Say VR is equal to A sine theta R and VD D sine theta D. And then here we will have say intermediate output, intermediate because this will ultimately go to the loop filter. So here we will have VM, which we know that is going to produce or going to contain rather a product of this reference and the difference signal in addition to various other components. We have seen this from the various circuits of the mixer that it very rarely produces only these two components. That means product of VR and VD. It will produce some other components also. So of course some filtering will be required, but if we do the filtering, this will be actually equal to A sine theta R into B sine theta D. And of course there could be some additional factor or conversion gain of the mixer. Now here we see that this becomes GCAB in divided by 2 into sine theta r into sine theta d. And this can be then expanded to give rise to cos theta r minus theta d minus cos theta r plus theta d. Now we can see that we have here a difference of the phase of the two signals, but it is actually inside cos function. And what we want is a difference to be explicitly visible, present, so that it can be then converted into voltage form. In general, we will not be able to get only this much part, but under certain special condition, this difference term can be extracted, and then other times can be neglected with the help of filtering. So here, let us assume that we have this scenario that this uh, theta r minus theta d is equal to say pi by 2 minus a small here. So this is small. So it says that we are assuming that theta r and theta d, they are almost at 90° to each other. So if this is the scenario, then we can see that this Vm becomes cos here. So we get this expression. Now here we can see that this can be written as this cos becomes sine. In fact, this will also become sine like this. So here, since we have taken this delta theta very small, so that the two phase are close to 90 degree, so this term can be approximated. And then we will have approximately delta theta minus, and this also can be then approximated in this way. So here what we now have is GCAB by 2 delta theta minus sine 2 omega d t. So here we have a function which is very small, and here we have a high frequency component. So if we pass this VM through a low pass filter, so if we do this low pass filtering, then what we will have is output which will be proportional to, so this VM, then what we will get on this side is a factor K into delta theta. So this factor K will contain this and some additional factor arising because of this low pass filter. So now we will have output voltage, and this voltage we can call as VE bar. So using this mixing and under condition that the two signals, they are almost at 90 degree, we will be able to produce voltage which will be proportional to the phase error. That means the orthogonal type of phase error. So here we will have this scenario. So if this is omega d, then omega r is going to be like this. So this is going to be almost 90 degree. Right. So here we can now plot what is called phase characteristic, phase detector characteristic. So in the phase detector characteristic, what we do is we plot this VE bar versus phase error. So here for this case, so we find that if the phase error uh, is around 90 degree, then we will have this kind of relation. And this phase error has to be very small, around 90 degree. So this is that means if the phase error is large, then this multiplier based phase error will not be able to produce a signal proportional to the phase error. So it will not work. So this detector is able to detect the phase error and produce a desirable voltage which can be fed to the VCO and allow the loop to get locked. But then drawback is that it should be phase error amount should be very small, in the neighborhood of 90 degree. Then only it will be able to work. So in general, this is the problem with the analog phase detector. So we are now going to talk about uh, digital phase detector. Uh, that means the signals are now going to be a digital signal. That means square wave. So before that, we will try to see that what do we mean by the phase of digital signal. We will try to interpret the digital signal also in terms of the phasor undergoing circular motion. So first we will see square wave. So say we have this square wave between 0 and 1. Say VR, and we want to know that what do we mean by this phase of this. For the analog signals, sinusoidal signals, we interpreted the sinusoidal phase as the angular displacement and strength of the signal as the projection on y-axis of phasor rotating with angular velocity omega. When we take sinusoid, this projection becomes the uh, strength of the signal, and this angular displacement is the phase. But what about this square wave? How we are going to interpret the square wave in terms of this? Because we saw that the functionality of PLL and the phase detector was very well understood in terms of this motion. So here what we do is we say that whenever this phasor is in the first half, that means starting from angle 0 to pi. So whenever it is between this range, the phasor will be in the upper half, and whatever may be the projection, we will always take projection equal to the full range. That means this much. So whenever it is in the positive half, we take this portion as the projection equal to 1, and we will call it 1. We will not take the its exact value which we do with the sine function. Similarly, when the phasor is between this say pi to 2 pi, that means when it is in the lower half of this motion, then projection is going to be negative, and we will treat that entire negative value. That means any projection value in this entire negative range as 0. Or we can take this as -1 also. So we can have a square wave between -1 and 1 or between 0 and 1. So both are possible. So here we see that the entire phase corresponding from 0 to pi corresponds to value equal to 1, and the phase corresponding from pi to 2 pi corresponds to value equal to 0. So we see that the same phasor movement can be used to interpret the square wave also. But unlike the sine wave, we do not have a strength which will vary with time gradually in smooth way. There is abrupt change in the value. So here we have, so this is one way of interpreting. Second way is that one can say that you take this sine wave, and whenever this sine wave is positive, you approximate it by 1. So for this entire range, you take it as 1, and whenever it is negative, you take it as 0. So this is another way of interpreting the square wave in terms of sine function. So now we want to know that if we have two square waves, then what shall we do so that we are able to sense the phase difference between them. So we can now take two phasors and with some phase difference between them. And then we will take one specific digital circuitry and try to interpret its output for the detection of the phase error. So here, let us say that we have here our phase detector, and then we have a square wave VR with a phase theta r, and we have a difference voltage coming from divider with phase theta d. So let us say that at t is equal to 0, we have this scenario that omega d is somewhere here. So it has some negative phase, and omega r is here with certain positive phase. So now we can see that the theta e is theta r minus theta d. So this is going to be actually plus of theta d because theta d is negative. So now we have this scenario. So here we can see that this is the scenario at t is equal to 0. So at t is equal to 0, the omega r or the VR signal is going to have projection equal to 1. Its value is going to be 1. However, the value of omega d, that means VD signal, is going to be equal to 0 because it is in the lower half. And omega d or the VD signal is rotating in this direction. So after some time, it will attain 0 phase and some positive phase. That means it will become positive after a certain uh, delay. After certain positive delta t, the VD will become positive. It will become 1. So now if we plot these two waveforms, so this is what we are going to get. So here we have theta, and first we are going to plot VR. So VR is already 1 at t is equal to 0. In fact, it became 1 at a moment before t. That means in negative t, it becomes 0, and then it will remain 1 for a significantly large duration. That means this much portion. So omega r or VR rather is going to be a waveform like this. So it becomes 1 before t is equal to 0, and it remains 1 for still longer duration. So this is a VR. Now we see that this VD has 0 value, and then it will become 1 after a certain positive moment. So after acquiring certain phase. So for this case, so this is theta axis, or this is equivalently can be interpreted as time axis also. So it is 0, and then after a small duration, it will become 1. So this is going to be the waveform for VD, like this. So these are the two waveforms, and now we want to know that what exactly is the phase difference between them in terms of waveform. So here we see that as this omega r increases, the phase error between them, phase difference between them is going to increase. So at this moment, if we try to capture a quantity which is gap between these two rising A's, so that will give me the idea of the phase error between them at this moment. So here. So suppose this theta r were here, then what will happen is this rising edge would have been here, and then there will be more gap between these two edges. So it is the gap between two rising edge of the two square wave, which gives the idea of the phase difference between the two waveform. So we now need to perform a certain mathematical operation or Boolean operation rather on this VR and VD such that we get output which is proportional to this difference between their edges. So actually there are various ways of doing it. We will start with the simplest circuitry. So let us see whether XOR gate can do this task. That means XOR gate as a phase detector of course, the digital signal. So here we have XOR gate, and what we do is we feed it with the two signal, and then we want to see that what will be this VM in this case. And for XOR, we know that we are VD. So we are going to get this output. So now let us try to see that what will be the output for this case. So we will draw the output here. So here we see that over this duration, one of them is 1, other is 0. So we are going to get high for this portion. And then for this much portion, we are going to get 0. And then again high, and so on and so forth. So for one cycle, so one cycle of say input VR or VD will correspond to this much duration starting from here to here. So this is the first cycle, and then this is going to be cycle number 2. So here in fact we have taken the frequency of the two cases to be equal. So omega r is equal to omega d. So we just wanted to see that what corresponds to this phase error. So we concluded that the uh, difference between the rising edge of the two signal gives the idea of the phase error between them. So, so over one cycle, you can see that we have two pulses, this P1 here and P2 here. Now here, suppose we try to shift this rising edge of the second waveform to here, then in that case, we can clearly see that the pulse is going to be wider. So if we shift rising edge here, that means we have shifted the waveform in this way. Then in this case, now we are going to get a pulse which is going to be wider. Like this. So we see that as the gap between the two edge increases, that means the phase error increases, the width of these two pulses increase over one cycle. So this is one cycle. Now, if you take the DC content of this waveform, Vn, which is XOR of Vd and Vr, then that DC is going to be proportional to the width of these pulses. That means the DC of Vm is going to be proportional to phase error theta E, which is equal to theta R minus theta D. So this is a very important relation. So what we need to do for detecting the phase error or the gap between the two digital signals is find out the circuitry which will be able to give you a pulse or again a digital signal such that the DC content of that digital signal over one cycle is going to be proportional to the phase error or the gap between the rising edge, which is proportional to the phase error. So this DC of this is also equal to phase error and gap between the two rising edge. So it is this idea which allows us to find out the other suitable phase detectors. But here we have considered the XOR gate. So now what we will have to do is feed the output of this XOR gate to a circuit which will give me the DC. That means do the low pass filtering. So this XOR gate output will be now fed to low pass filter, and then what we are going to get is VE bar. So uh, D, this VE bar is actually DC of VM. So now we will get VE bar is equal to K into theta error, the phase error between the two signals. So now we want to know that what will be the uh, characteristic graph of this type of phase detector. So when we plot the characteristic graph, as was pointed out, we plot on y-axis this V bar and phase error on x-axis. So this allows us to know that what is the range of phase error that can be tackled by this phase detector here. So we are seeing the characteristic of XOR gate, but keep in mind that this is basically the characteristic of XOR gate plus L low pass filter system as a combined. So sometimes this combination itself is called the phase detector, but uh, actual job is being done by this circuitry, and this simply extracts the DC part of it, which gives the correct idea of the phase difference between them. So now we want to know that how this graph will look like. So here we can see that when the phase error is 0, that means when the both the uh, plots coincide. In that case, the output is going to contain no pulse. Right? So that means if we have, say, this kind of signal, here. So this is VR, this is VD. So now when we do the VR XOR VD, so what we get is ideally 0, nothing. So we are going to get 0. Now when this uh, say phase difference between them increases, say for example when we have this kind of VD, so now we are going to get narrow pulse over one cycle here. And as this phase error between them, or the gap between these edges, this VR and VD increases, the pulse width is going to increase. So as this width increases, so is going to increase this pulse width like this. So we see that the DC content will increase with the page error in this way. So then question arises, to what extent this will increase? So here we can see that the maximum shift that we can introduce between these two signals is equal to uh, pi. So in that case, we will have this scenario. So our pulse or VD would have shifted like this. So this is new VD. So we can see that for this case, what we are going to get is pulse which will be high for the first half and then high for the second half as well. So this is the maximum anti-overlap. So we know that XOR basically checks the anti-overlap. That means moment when one is high, other is low. So this waveform is going to increase for phase error equal to pi. Up to pi. Now what will happen if this gap between the two edges is more than pi? Then what will happen is you can see that we will have now this kind of waveform. This red color. So here you can see that now we are going to get output which is going to be now narrower than this green case. So now we are going to get output which is going to be like this. Right. So here we can see that the pulse width has decreased, and as we now further increase the gap between these two edges from pi to 2 pi, this pulse width, this width is going to decrease from t by 2, where t is the complete cycle, from t by 2 to 0. So what we are going to get is now a response like this. And this phenomena will then repeat like this. So this is the phase characteristic of XOR gate phase detector. So here you can see that this phase detector is able to detect phase error up to pi. So we wanted this kind of relation, B E bar is equal to K into theta E. So the phase error should increase when the theta E increases. And it is over this portion that we see that characteristic is visible. So compared with the analog phase detector, we find that this XOR gate is capable of detecting wider range of phase errors. But only thing is that now we will have to ensure that these two signals, they are the distal. So here a phase error which can be detected, and be between this range. So in the next lecture, we will see that how we can come up with a circuit which will have even wider range of phase detection capability. So what are other digital circuits which can do that?